Hello, everybody. Back again, continuing with the nycFlights 13 baseball database practice. We are on line 194 of the file and now going to talk about joins in SQL. Say that we want to find the 5 most common destinations from JFK in 2013. But we would like to provide the full names of the destination airports, not just their 3-letter codes. How might that work? In dplyr, it could go like this. You start with flights, you filter for the origin to be JFK, and then you group by the destination, and then summarize using that call to the end function. Your summary variable is the number of flights, how many rows were in each group, each destination group. And then to get the full name of the airport, you would need to get that from the airport's data table. So you'll do an inner join with airports, but you don't really need all of the columns of airports to join in with you. You just need the FAA column that has the 3-letter airport code and the name column that has the full name of the airport. So I'm doing an inner join of airports selected for those 2 columns. How am I doing the join? That's given by the by parameter. I use the dest column in flights because that's the 3-letter code for the destination. And that links up with the 3-letter code for the airport in the airports column. After that, I only need the full name of the airport and the number of flights that went from JFK to that airport. I do want to arrange in descending order by the number of flights and look at just the top 5. And so here are our results. Now, how might we do this in SQL? Well, SQL has a join keyword. So other than the slightly backward way of SQL compared to dplyr, it's fairly simple. So we're going to be doing some selections from flights, abbreviated here as F, but that selection is going to take place after we join it with airports, abbreviated as A. On is kind of like the by parameter in dplyr, on F's destination column with A's FAA column. In that backward way, the filtering for the origin to be JFK is stated after all of this. So is the group by. And then we order by number of flights descending, and here's our head. So let's just see how that will work. Will it give us the same results? Indeed, it does. Now, in the example above, we were joining on that entire airports table that had a lot of other columns giving information about those other airports. That was really more than we needed. In very large data tables, queries that do this could become kind of long to accomplish. Wouldn't it be nicer to join to a smaller data table? We can use the concept of a subquery to do that. Check out the join in this approach. Instead of joining to the entire airports, we join on the select of FAA and name from the airports. That entire operation is in parentheses, making it what we call a subquery. And it's that result that is abbreviated as A. Otherwise, the SQL code is the same as in the previous example. Let's watch it work. Yep, same results. So remember, subqueries, parentheses, they can come in handy from time to time. Here's a more elaborate data wrangle in SQL. Say you want to find the number of flights, the number of canceled flights, and the percentage of canceled flights from each New York City airport. Now in dplyr, the wrangle might go like this. Start with flights and create a new column that records whether or not the flight was canceled using the mutate dplyr function. And cancel is just the result of a call to if-else, where the Boolean condition is whether or not departure time is non-assigned. When the dep time is not assigned, the flight never left and was thus canceled. We'll write a 1 in that column if so, but if the dep time is not unassigned, the flight left, we write in a 0. So then we can group by origin, and when we summarize, the call to end tells us how many total flights there were in each origin group, but we can sum up canceled, and adding up all those ones counts how many flights were canceled in each group. That comes on as the variable num canceled. Once we've got that summary table, we can create a new column in it called percent canceled, which is just number canceled divided by number of flights times 100. So in dplyr, it's not so bad. With SQL, it can get a lot more involved because in SQL, there's just no way to just add on a new column like we did with mutate here right at the beginning of our wrangle. Instead, every sort of new variable that you create has to be created sort of on the fly mid-query. So to illustrate how this might go, let me give you a simple query that doesn't do the entire task. It just gives us a little start. From the flights data table, we're going to select the flight number, the scheduled departure time, the month, and the day, but we're also going to select a complicated transformation function and call it the canceled. What is that transformation function? It's all of this stuff. So it involves the case keyword, which functions a lot like if-else. When the variable dep time is null, and that's how NAs usually are going to be registered in SQL databases, then it's a 1. Otherwise, it's a 0. That's what the canceled is going to look like. So let's run this and see what we get. Notice I didn't set any limit on the results, so officially it's supposed to bring in the whole results of the query. Now, R is a little careful, and it only brings in the first 1,000 rows, so you don't get overwhelmed. So that's why limit can be important in mammoth queries from big databases. But anyway, we do get this new variable, and it's mostly zeros down here because most flights don't get canceled. Okay, so what's the idea? Well, we can combine the case idea with the notion of subqueries. So we're going to be selecting from flights, abbreviated as F, joined with the results of this subquery here. That's the same subquery that we had before, and we're abbreviating that one as T. We're doing it where the flight number from the F data frame is hooked up to the flight number from the T data frame, but also the departure time has to be the same and the month and the day have to be the same so that we get down to exactly the right flight, and the group by origin coming at the end. Now see how the selections work. So notice that we start having to refer to what data table a variable came from. And so we select from the origin variable in F and call that airport. The sum1 is counting up the number of flights. The sum of the canceled variable from the t part of the join comes in as the number canceled. And then to get the percent canceled, then we take the sum of the t canceled variable, that's the number canceled. We divide by sum of 1, that's the same as number of flights, multiply by 100 to make it a percent. Now you see a little bit of something new in here, times 1.0. Mathematically, that doesn't change the sum. Why do we have it in there? We'll talk about that later. But let's see if this works. Takes a wee while, but we're okay. So about 2.6% of all the flights from EWR got canceled. So again, in a later screencast, I will explain how come we needed that 1.0 multiplication in the call to the sum function. Here's another interesting keyword in SQL. Suppose that we want to restrict our analysis of the mean arrival delay that we did earlier to those destinations to which there were at least 100 flights. Okay, so we don't want to look at the average delay for destinations from our New York City airports that were, that were very uncommon. We just want to look at the common destinations. So the keyword having is our friend here. So similar query to what we had before, where we've filtered down for the origin to be JFK, and we're grouping by destination. And here we are counting up how many flights were from each destination and computing the mean arrival delay just as before. But there's this new line inserted in the query after all of the where and the group by. Having num flights bigger than or equal to 100. So once num flights has gotten defined in this selection here, SQL is able to cut down the table to just the ones where that variable is bigger than or equal to 100. Then it'll order by and limit. And so you get rather different results than in the previous query, because now we're only looking at airports that were common destinations. Okay, we're done working with the airports data. So why don't we go ahead and disconnect from the little database that we have built. There we go. Let's do some practice with the baseball data from the Lahman package. So I'm going to library Lahman, and I'm going to set up a connection to a new database, call it con. So that should enter into our global environment over here. And let's write the tables of the Lahman package into it. The batting table, the pitching table, the Hall of Fame table, the master table, and the teams table. So here's a task involving joins. Find the full name and number of home runs hit by the home run leader for each league for each of the seasons from 2000 to 2004. So we are already familiar with the concept of joins here. We know that we're probably going to be joining the batting table with the master table on the player ID variable from the batting table matching up with the player ID variable from the master table. That part's fairly familiar. If you want the full name, though, then you're going to have to stick together the first name from the master table with the last name from the master table. I decided to put a space between them. Notice how the double pipe is using to paste together those variable values, and the result is being abbreviated as name. Just remember, the double pipe is for SQLite only. In MySQL, you'd be using concat. Let's just see if this works. Great. So here's the equivalent thing in MySQL with the concat function. Next up, find the names, the debut dates, and the career batting average of all players who had more than 6,000 at-bats and whose career batting averages are over 340. Arrange the players in descending order of their batting averages. So this is just another illustration of the having keyword. You want the average that you have computed in this transformation function here to be bigger than 340 before you'll start considering the players, and you want their at-bats to be bigger than 6,000. So notice apparently SQL has a round transformation function that we're using here to make the output a little nicer. We're summing up the number of hits. Here's that mysterious times 1.0, and then dividing by the sum of the at-bats to compute the batting average, but we're rounding off to 3 decimal places. That's what we call the batting average. Let's have a look. There we go. So let's now discuss why it is that we did this mysterious 1.0 multiplication. If you wanted to do arithmetic in SQL, you actually have to enter it as a query. Everything in SQL is entered as a query. So you would actually say select 5 divided by 2. And let's see what happens with SQLite when we do this. Well, that's wrong. 5 divided by 2 is 2.5. Why are they saying 2? It's because SQL by default is going to do integer division, meaning that it's going to say how many times 2 goes into 5, forgetting the remainder. And 2 goes into 5 twice. So that's why it's the answer. But you can force SQLite to recognize that you want to work with decimal numbers by including a decimal number in your computations. 5 times 1.0 says, no more integer division. We do floating point division, and we get the 2.5 that we expect. So in any SQL system that you work with, if you're not getting the arithmetic you expect, consider the possibility that it's doing things like integer operations instead of floating point operations, and you can consider this kind of coercion. It will usually work. Here's another one. Find all players who hit more than 50 home runs in a season, but who have not ever served as pitchers. Order them by their career home runs in descending order. Okay. So here, the kind of the new thing is that these people, we got to go to the ones that have never served as pitchers. So, for example, Babe Ruth should not make it onto this list because he served as a pitcher early on in his career. So the key is that once you do the join, you want to knock out the ones whose player ID from this draw from the pitcher table that got abbreviated as P. You want to do it where that's null, and that will siphon off the ones who served as pitchers, and you're only looking at the ones who did not serve as pitchers. You see, after you do a join, if you've got some batters that did not serve as pitchers, then their player ID is going to show up as a null, and so that's a nice way to capture them. Let's give this one a try. Yep. Here we have find the 10 pitchers who have stolen the most bases in their role as batters. Okay, so here we start with batting, but we join it with master on the batting player ID being the master player ID. But we just want the ones who were served as pitchers. So we want to filter down for where the batter player ID is in the result of selecting player ID from pitching. So this is a cool new keyword in that's kind of like the %in% in R. Result of the query works out. So go ahead and study those queries in more detail. They can give you useful hints on homework. Just make sure that you recognize the differences between this and MySQL type databases that you might confront in homework. We will always politely disconnect from our database connection. And just to point something out, you could totally knit this stuff up. No problem at all with that. I'm going to go ahead and make this a bit smaller and just run the knit so you can see that it really can work. There you go. The tables are all the SQL queries are all nicely displayed using a knitter cable function under the hood in R Markdown. So that can be very nice to study by. All right, we'll see you next time.